So welcome to part two of electrophilic addition to alkenes, where we're going to focus on the mechanism, specifically the carbocation formation process. If I were to have a alkene, now keep in mind we're going to have two hydrogens here, and one here, and I were to add HX. The nucleophile is going to be our alkene because it is electron rich. It has that double bond, those pi electrons. Our electrophile is going to be our HX, our acid. Nucleophiles are bases, electrophiles are acids. Nucleophiles are electron rich, electrophiles are electron deficient. So the reason why this is an electrophilic addition because we're adding an electrophile to our double bond. But remember, when we show mechanisms, we're showing the flow of the electrons themselves. So to start, we're going to take those electrons in the pi bond, and they're going to be attracted to our electrophile, and specifically the hydrogen. The double bond then, or the single bond here, must break to complete the process, and what we're left with are two scenarios. We could add the hydrogen to the left side here, or we could add it to the right, putting three hydrogens here now. Now keep in mind, these two carbons were the ones that lost electrons in the process. They did not pick up the hydrogen. So what's happening here is they lost a bond. They're going to be positively charged. In one scenario, I have a primary carbocation because the carbon that has the charge is only bonded to one other carbon. And in the other scenario here, my carbon is bonded to two other carbons. It is secondary. The other piece that we're missing here, which is going to be the X minus, we'll see where that comes into play in the next step. But before we do, we have to decide which of these two intermediates is more likely. Remember, the more substituted, the more stable. Secondary is more stable than primary. So the secondary carbocation is actually what is going to form. And when I draw that, I'm going to draw it without the hydrogens, so it's going to look like that. So let me go ahead and draw that product. Again, we're going to draw that out without all the hydrogens, and that's what we get. We're also going to get X minus, as I mentioned. We lost that X, it's going to be over there. Now we kind of have a role reversal now. This was our nucleophile, or you can also think of nucleophiles as bases. They produce conjugate acids. So now this is our electrophile. Our acid or electrophile to begin with is going to then become our conjugate base or our nucleophile. So now we add, whoops, not there. Now we add our nucleophile to our electrophile, and X is going to go here. We call this process Markovnikov's rule. Markovnikov's rule really states that the more stable carbocation is going to form. But one thing you'll notice is in order to form the more stable carbocation, you're going to add the hydrogen to the carbon with more hydrogens. This carbon had two hydrogens, whereas this carbon only had one. So we generally state Markovnikov's rule as that which has gets. The carbon with more hydrogens will pick up the hydrogen, meaning the carbocation will go on the carbon with fewer hydrogens. And in the end, our X will go on the carbon that had fewer hydrogens. The carbon with fewer hydrogens is the more substituted carbon. This carbon had one carbon attached, this one had none. So again, we're going to, in reality, form the more stable carbocation, But to simplify it, we're going to add the hydrogen to the carbon of the double bond with more hydrogens and add X to the other side. So if I were to have something like this, again, adding HX, this carbon has no hydrogens, this one has two. So I'm going to add the hydrogen here and X there. And this would be my product. That is Markovnikov's rule. In the next video, part 3, we're going to move into rearrangement possibilities because when we form that carbocation, it is possible shifting a hydrogen could produce a more stable carbocation.